All right, today we're going to do something a little different. We're going to tell a story. You know, a classic tale, a hero on a quest faces an impossible challenge and discovers a secret power that changes everything. The only twist? Our hero is an AI. So let's dive into this little epic, deep into the world of reinforcement learning. It all kicks off with this single, absolutely massive question. How do you prepare a machine for something it's never encountered? How can it possibly learn to make these brilliant winning moves in a game that has more possibilities than you could ever memorize? This is the riddle our hero has to solve. Every great story starts with a pretty simple goal, right? Well, for our hero, a reinforcement learning agent, the quest is crystal clear. Find the rewards. So let's meet this hero and get a feel for its world. Okay, so this diagram here, that's basically our hero's whole existence. It's a system designed to interact with its world, which we call the environment. Our hero, the agent, tries something. It performs an action. The world reacts, and in return, maybe, just maybe, the agent gets a reward. It's this simple little feedback loop. And the mission? Get the highest score you can by just learning as you go. And this whole song and dance, that's what we call reinforcement learning. You see, it's not about being told the right answer from the get-go. No, it's all about trial and error. Honestly, it's a lot like teaching a puppy a new trick. Good actions get a treat, a reward. Bad actions, you get a penalty, or maybe just nothing at all. So in the beginning, the world seems pretty manageable. Imagine this simple little grid. Most of the squares have a reward of 0, zilch. But one has a big prize, 100 points. All our hero has to do is figure out the best path to that prize. Sounds easy enough, right? But then, our hero discovers a pretty terrifying truth. The world isn't a simple little grid. Oh no. It is vast, it is complex, and it is impossibly, mind-bogglingly large. And that initial strategy? It's about to hit a serious wall. I mean, think about it. Learning would be a piece of cake if you could just remember the outcome of every single possible choice you could ever make. You'd basically have a perfect cheat sheet for life, right? And here it is. This is the central conflict of our story. What happens when the number of possible situations our hero could find itself in is bigger than any memory could possibly hold? This is where the quest gets really hard. Let's look at a super simple example just to see how quickly things can get totally out of hand. Let's say we're trying to learn a concept. What makes for a great day to go play in the water? We've only got 6 factors here: the sky, the wind, and so on. And this number, this is the wall our hero smacks right into. For that tiny little water sports problem, there are over 5,000 possible rules to check. If our hero tried to memorize its way through that, it would fail, period. And that's for a tiny problem. For a real game like chess or Go, the number is, well, it's just astronomical. Memorization is just not going to happen. So, with its only strategy completely shattered, our hero is lost. But then, it stumbles upon a secret, a totally new way of thinking that's about to change everything. This, my friends, is the power of generalization. This is the crucial choice, the fork in the road. Does our hero try to memorize every single turn on every single road, a tangled, useless mass of disconnected paths, or does it learn the underlying structure of the world? Does it learn the map itself? So the old way, memorizing, it's kind of like this. It's just a list of disconnected facts. It's clunky, it's inefficient, and it tells you absolutely nothing about a day you haven't seen before. Like day 3, useless. But generalizing, oh, this is the game changer. This is about finding the pattern, the underlying rule. Sunny days with strong wind are good. See? This one simple idea covers a bunch of past experiences, and, this is the important part, it lets our hero predict what will happen on a new day. It hasn't memorized the path, it's learned the map. So just like that, our hero gets a new tool. Let's call it the generalizer. Its job isn't to just store a bunch of old examples. No, its job is to take those examples and create a hypothesis, a general function, a map, that actually explains them and can predict the future. Okay, so armed with this brand new power, our hero is finally ready for a real challenge, a foe worthy of its new skills. Let's turn to the game of checkers and see how this all comes together. You see, the problem is the same, but it's been scaled up to a massive degree. We're talking billions upon billions of possible board layouts. Trying to memorize them is just a joke. So how can the hero possibly look at a board it's never seen before and decide which move is the best path to victory? Well, it does it by looking for clues. Instead of trying to remember the whole board, which is impossible, it just looks at a few key features. How many pieces does each side have? How many of those are kings? Who's under attack right now? These features kind of summarize the whole state of the game.
And here it is. This is the secret formula. This is the map for the game of checkers. It combines all those features we just saw into a single score. The X's are the features, like the number of pieces, and the W's, those are the weights. They basically represent how important each feature is. Like, is having an extra king more important than having 2 extra regular pieces? The weights will decide.
This entire technique, this whole approach, actually has a name. It's called function approximation. And really, it's the beating heart of generalization. Instead of trying to build this massive, impossible table that links every single board to a score, we just approximate that table with one single, flexible formula. So, how does the hero figure out the right weights for its formula? Simple. It learns from its mistakes. After making a move, it compares the score its formula predicted with a better estimate of what the score should have been. If the prediction was too low, it nudges the weights up a little. If it was too high, it nudges them down. And slowly, over thousands and thousands of games, it tunes those weights to perfection. And there we have it. Our hero has mastered the game. It conquered this impossibly large world, not by memorizing, but by learning to generalize. So now it's time to bring this power back from the world of games into our own. So if you boil it all down, the ultimate lesson of our hero's journey is this exact contrast. On the one hand, you have this house of cards built from memorized facts. It's brittle, it's fragile, and it's totally helpless against anything new. But on the other hand, you have this living tree grown from general principles. It's strong, it's efficient, and it can adapt to a world it has never seen before. And look, this isn't just about games. This power to generalize is the magic that lets an AI learn to drive a car, where no 2 moments on the road are ever exactly the same. It's how these systems optimize massive factories, discover new things out in space, and yes, play board games at a level that can challenge the best human players on the planet. Our hero's journey taught us that true learning, real intelligence, isn't about memorizing the past. It's about building a model that can predict the future. And that leaves us with one final, kind of mind-bending question. That AI learned to generalize inside a game with set rules. So what happens when it starts generalizing about our world? Thanks for watching.